Good morning. Welcome at the lesson 10. Welcome at the first session. Thank you for joining me. Where is the chat box? Yes, hello. How are you today? Is everything okay in these challenging days? Okay, okay, that's what all of my students, are telling me. Okay, that means I'm really hoping that everybody is, of course, well and healthy, because that's the priority, that's the most important thing. And then we can focus on calculus, right? Okay, that's what we have. We do have the last two sections in chapter 3, which we will still talk about the application of the derivatives. And today is really nice application, optimization problems. And actually tomorrow we will cover the last section in chapter 3, and we will talk about anti-differentiation. Okay, that means something backwards, in which probably most of you know the proper way. I mean, anti-differentiation is also a proper terminology, proper name, but we also have another one. Okay, that's me today, optimization, and tomorrow the reverse process. Instead of differentiating, we will be anti-differentiating. Or I always want to say anti-differentiation, but yes. Okay, optimization problems today. That means what we will do. Actually, what do you think? Optimization, what this means? We do have a short description at the bottom of this slide, but like optimize something. Do you think you can tell me? You can, of course, type it. Like what this means to find the optimal solution. Yes, yeah. We have to find the maximum minimum, which I will always think that maximum minimum is like extreme solutions, but that's actually the optimal solution, the best solution. Of course, not everything we want to maximize, not everything we want to minimize, yes, but did I type? Yes, I type it. We do have some things that we really like to maximize, profits, some volume, maybe areas, or sometimes we would like to minimize a distance, time, yeah, to be more efficient, which I'm not fan of speeding up. And cost, of course, cost. Yeah. Okay, that's the optimization problems. And the optimization problems, of course, are the word problems. That means, again, the same thing like for the related rates. We will see the word problems, we have to read, understand everything, what they're giving us, what they're asking for, and yeah, put everything together, which means combine them in the equation, in the model, and then solve it. And since the maximum minimum is involved, probably the derivative will be involved, yeah? Because we know how to find the maximum value. Not always, like some of the endpoints are giving me maximum or minimum. We always have to look at the critical points and the local maxima, minima. Okay. Okay, I do have steps. Of course, the same, almost the same like for all of the word problems. We have to read and understand, draw something if it's applicable, if we can draw. I always like to draw the situation. Having a picture, having some draws, we can introduce, we can label everything, we can introduce notation. We have to know what is given, what is required. And now we will require, in this case, okay, it will be probably like we have to, this is optimization problems, that we have to maximize or minimize. That we have to determine, yes, if we are maximizing or minimizing the problem. And not always we will have the explicit way, like this will be not explicitly stated. That's when we have to always read not between the lines, but we have to like figure out if we're really maximizing or minimizing. And then we always have to create a function, okay, like a model equation function in terms of one variable, because that's calculus one. And then having a function, we can definitely, because it will be much easier, we can definitely maximize or minimize. We can find the maximum and minimum value, which of course means that we have to look at where we are, domain, we have to differentiate, and then critical points, and then maxima or minima. And always at the end, especially for multiple choice question, we really have to get back to the original like text, words, and actually find what we're looking for. Because sometimes we will look for the entire function, like what is the maximum value of the function. Sometimes we have to find out what value of x will give me a maximum. That means depends. Yeah? I don't want you to choose the wrong answer. Okay, but for now, no multiple choice, just the problem. Okay, I just copy from, I think this is from 3.1 or 3.1, the first derivative test. But of course, we know how to find out if function is like increasing, decreasing, we know what is on the top, decreasing, increasing. That's just mathematical symbols, but it's nice and easy. Oh, okay. That means we have example number 1. I think I have 4 or 5 examples for today. And I still didn't grade it, but thank you for doing the optional assignment, the graphs. I really like your graphs and all of the points, the guidelines for analyzing the function. That means thank you. I did look at some of them, but I still didn't put the grades, probably today or tomorrow, but good. And if you like, I can maybe assign another extra points assignment this week. Yeah, if you like, you can tell. I can see now. Okay, because I know that always in this last like, it's not last minute, but in this at the end of the semester, we like to boost the numbers. Okay, that's what we have. A farmer has 2,400 feet of fencing, and he wants to fence off a rectangular field that borders the straight river. Okay, he needs no fence along the river. And now is the question, what are the dimensions of the field that has the largest area? That means we can see based on this question, what do you think? Overall, we will maximize something or minimize in this question? We will maximize. Thank you. Thank you. Noah said correct, and Yatniel said, yeah, maximize, because you can see, that's what I said. We will not have the explicit way. It says we have to find the largest area. Actually, no. We don't even have to find the largest area. We have to find the dimensions. What are the dimensions of the field that will give me the largest area? And yeah, you probably saw it's something like this. Yeah, we can see we do have a river, and then 2,400 feet only of the fencing, no fencing along the river, and then we have to figure out. Of course, we will not like draw, and we will not try to compute the areas. No, we will use the calculus, but maybe like this one. 100, 100, 2,200. But that's the area. That's even bigger. That's even bigger. Okay, that's what we will see. And this is, of course, the general graph. Yeah? We will name x and x, the width, y will be the length, or the other way. And we have to define a function which will represents the area, and then work it out. But we can see that's how, definitely not this, but we will not do through the trial and errors. Okay, let's come back to the question, and this is the picture. And that we can see. In this case, we can draw it nicely. Okay, and the given information is, of course, only 2,400 feet of fencing. Feet. Okay. Okay. If it's 2,400, then it would be nice to define this 2,400 in terms of our labels, our variable. That's what do you think? Using x, and y, I mean x and y, how can I define a fencing, which I can say kind of like parameter, but with one extent. It's 2 times x and y. Thank you. Yeah. Okay. Now we will, like you said, we will maximize area. And as soon as we know this, we will also need the formula. Who can tell me what's the formula for A? For the area of the rectangle? Can you, yes, just length times width. Yatniel, do you think you can replace, yes, like L and W with X and Y? Of course, yeah. Okay, that means this is definitely our function. That's our function, X times Y to be maximized. However, we don't like function of two variables at the moment, X and Y. We have to, let's say, replace X in terms of Y or replace Y in terms of X. And how can we do this? Of course, we will always use the given information because we know that 2,400, that's 2x plus y. And I think it's easier to solve for y. Okay? That means y equals to 2,400 minus 2x. And then I can take this formula and substitute instead of y. And then I have really nice function, like a one variable. X times y, but y is defined as a 2,400 minus 2x. And I can just distribute. That means my function to be maximized is this one. Quadratic function, nice and easy power function. 2,400x minus 2x squared. That means we probably know one thing that is important. Because of that 2,400, we do have some restriction. Okay? That means probably looking at how y is defined, 2,400 minus 2x, like we can't accept any numbers. X and y, of course, must be positive because that's length, yeah, based on the common sense, the geometry. That we can see 2,400 minus 2x, this quantity must be positive. That means this will give me some restriction, some domain. And I will, okay, I didn't type it, but let me, 2,400 minus 2x must be positive, okay? And then, of course, x is positive, but still this quantity, because if x is extremely big, or if 2x is bigger than 2,400, then I have negative and then doesn't make sense. We can't accept this. Let's just solve this inequality. I will subtract 2,400 and dividing by -2, I will get 1,200. But do you remember what we have to do with the direction of inequality? Flip it, because it's always when we're dividing or multiplying by the negative numbers. Okay, that's we can see x, of course, x is positive. I'm not even considering the negatives, but all of the quantity, we can't have values greater than 1,200. Yeah, that means this is my domain. But the thing is, I can't really accept 1,200. Yeah, I can't put equal to, because if x will be 1,200, I will have no fence for y. That means it's still like open-ended. That means we don't have to test like 0, of course, doesn't make sense, and 1,200 also doesn't make sense. That means the only extreme values, it will happen at the critical point. That's when we have to find the critical points. Okay, because we can see no endpoints are in the domain. Okay, critical points, we remember. We need the derivative. Derivative is just 2,400 minus 4x, and derivative is 0. If 2400 minus 4x is 0, then x, oh, okay, now I do have, do you see, I type it a little bit. Who can tell me the critical point, and I will rewrite this again. 2400, 1200. That means we have 0 and 1200. That's the only quantity. 600, okay, I can see on the, oh, I didn't finish, okay. X equals to 600. Okay, yeah, because 24 divided by 4, 600. Okay, that means 600 is definitely in the domain, perfect. And just because if this will be like a nice open-ended question and we would like to see each step, we have to put the 600 on the number line and test it. And we testing the derivative. 600, if I will pick a number greater than 600, like let's say 1000, and this is my derivative. I will have 4000 negative, I will have negative number. If I will pick like number smaller than 600, like let's say 1, 2400 minus 4, it will be positive. And then my function, which is the area, will be increasing, decreasing. Definitely maximum, and that's the only maximum, that's the only extreme values. That means at 600, this function will attain maximum, and that means this is the largest area. That we will have 600, and what is the final answer? What's the final answer? Because that's what, do you remember the last point? We have to always look what they're asking for. That means the final answer is 600 by, because we need dimensions. Dimensions. 600 by 1200. Let's check, because because y was defined as a 2400 minus 2 times 600, because we have to find out what is y, and of course 12. Okay. That means this is the final answer. If they will ask to find the largest area, then we have 600 times 1200. We have to just multiply. Okay, that's the way to go through the optimization problems. Yeah, this is nice question. Okay, let's see. Oh, this one. This one is, box question. Nice question. An open rectangular box with square base is to be made from 48 square feet of material. What dimensions, again, dimensions, will result in the box with the largest possible volume? Okay, that means again, we will maximize or minimize in this question. Of course, maximize, thank you. And we have to find the maximum volume, because we may build some box and like the capacity, I can say capacity, the volume, yeah, could be smaller, but we want the maximum possible volume. And we still have some restriction because we have only 48 square feet of materials. Okay, the same thing, given, required, and I draw a box, but doesn't look like square base, but I will label X and X, and let's say H. Yeah, that means that actually the bottom is the square, and we do not have, we don't have to build, we don't have to use the material on the top, just open. Okay, X, X, and H. And now, using X and H, can you tell me how 48 is defined? And what actually is 48? 48 square feet is the area, is the surface area. That's what we have. We do have at the bottom, we do have X squared, right? And then we do have 4 sides. And each side is a rectangle. x squared plus, thank you, Matt, x times h, because all of them are the same. Yes, x squared plus 4xh, really good. X squared plus 4xh, not just one x squared, yes? Just to make sure, because we don't have the top. Okay, now volume. Who can tell me the formula for the volume of the box? Yeah, that's not a really, do you remember the cone or something? Just x times h, which is x squared times h. Yeah, thank you. Good, good. And now the same steps. We do have a function, volume, we do have a formula, but x and h, we don't like two variables. We have to possibly rewrite h in terms of x. And I can place 48 here. I switched, and I can solve this equation for h. That means always to have to rewrite function in terms of the one variable, please use the given information. Okay, subtracting x squared and dividing by 4x. Am I right? Yes. 48 minus x squared. Okay, that means this whole expression will go here. Okay, x squared times this. I can simplify a little bit. Okay, I will simplify, but the same thing. That h, yeah, because of that 48, we do have some restriction. 4x in the denominator is okay, because x is always positive, but 48 minus x squared must be also positive. That means I have to say 48 minus x squared is always positive. And we can probably see, I mean, I did factor out nicely, and we can solve the quadratic inequality, but you can probably like think that if this is square root of 48, the numbers cannot be greater than square root of 48, because then I will have this quantity greater and everything will be negative. That means just numbers, of course, positive, okay, but not greater than square root of 48. And again, the endpoints are, they don't even make sense to substitute, to use them, because I can't have x0, but the endpoints are not included because it's open interval. The only extreme values will be at the critical point. That's we have to follow the same rules. We have to find out critical point and test it, and most likely will be maximum. If it's not maximum, then we don't have solution. We can't really figure out. Yeah, that's sometimes the case. Not yet. Okay, let's take care of the function. We can see x squared and 4x. I can simplify definitely 1x and that x. And I think I still see the product. I will distribute that x times 48 and x times x squared. Okay. And I don't know if I type this, but I will divide both of the terms on the top by 4. Oh, I didn't. Okay, because I was thinking if I will divide by 4, I can maybe keep it like that. Or maybe I can keep this way. 48x minus x cubed. Because the only thing that I want to rewrite a little bit, I don't want you to think that we have to use the quotient rule. As soon as it's no x, no variable in the denominator, it's not a quotient, it's just the constant. Okay? That means for the derivative, because we know we have to find the derivative, we don't have to use the quotient rule. That means 1/4. And then it's just the derivative of the top. 48x minus x cubed will give me 48 minus 3x squared. Okay? I hope this makes sense. And I still put the fraction, the quotient form, but we can see it's just 1/4. That's 1/4. It means only derivative from this part. Okay. And since it's no x in the denominator, we will not consider the derivative is actually defined everywhere, wherever is the function defined. We just need to find out where derivative is 0. And this derivative is 0 if this expression is 0, of course. Is this nice number or not nice number? We have to divide 48 by 3 and then take the square root. It is nice number because it's 16 and then, yeah, and then it's 4. Thank you. Thank you, Robbie, for calculating. Okay, that means we do have a friendly number for the even radical expression. 4, that means x equals to 4. I'm hoping, I'm testing, it will give me maximum. That means we will test, and we testing, I can use this formula. Yeah, looks good. That's the derivative, or even just the top. Okay, when I pick number greater than 4, we will definitely have negative, and less than 4 will give me positive. 48 minus 3, for example, positive. Okay, and then function is increasing, decreasing. Excellent. This is maximum. That means dimension, we will have x4, 4 by 4, the base, and who can tell me what will be h? Okay, that's again the dimensions. That's the final answer. H is defined, oh, that's h. Who can substitute 4? 48 minus 16, divide by 16. Is just 2? I think so. Yeah, thank you. Thank you, Matt. 48 minus 16 over 16. 32, it is 2. Okay, that means 4 by 4 by 2. That's the final answer. Okay, good. And that's it. That's both of the questions are quite, yes, quite, I don't know if challenge, but yeah, they include lots of stuff. But we can see the procedure the same. Okay, let's see my next question. Oh, okay. We have to know it's similar idea, but now the cost, the dollars are involved. Okay, that's we have to know. It's almost the same like the example number 2, but we have to add dollars at some point. Okay. A rectangular storage container with an open top, that's mean the same thing, but now it's rectangular. Is to have the volume, the volume is given, 10 cubic meters. Okay. The length of its base is twice the width. Some information for the good labeling. Materials for the base cost $10 per square meter. Material for the sides costs $6. Okay, a little bit cheaper because the bottom has to be always strong. Find the cost of the materials for the cheapest such container. That means we have to, okay, this is the information. And now, of course, silly question, but I have to ask, are we going to maximize something or minimize? That's first of all. Minimize, because we can see we have to, cheapest container. And what we will minimize? What kind of function we have to create? Minimize the cost. Okay. Let's leave it. That means because we will, that we have to minimize the cost, but in order to create a cost function, what we will use, like what formulas we will use, the cost of on y and the material, the amount of the material, which means like in terms of the mathematical terminology, we have to start with the amount of the material, amount of the area. Yeah, that means we will minimize the surface area, but of course cost. It's important to add the dollars before any like differentiation. We have to have a correct function. Okay, did I type this question? Okay, I typed a little bit. My pen is working. Do you remember last week was not working well? Okay, let's label. We can see the second sentence is telling me that the length of its base is twice the width. That means I can label for you x. How can you label the length? 2x, yes, that's when we can avoid And of course, I will put h. Okay, x to x, we know y to x. And, did I type this? Okay. And now, volume is given. Using our new labels, x and 2x and h, do you think you can tell me volume? What's the formula for the volume of the box? Of course, always. Yes, 2x. Oh, okay, I could, okay, 2x squared, because it's 2x times h, really good. Okay, length times width, yes. 2x times x times h, of course, 2x squared. Okay, now we know that we have to minimize the cost. And as I said, the first step will be the cost, of course, means the amount of the material as cheapest as possible for the entire box. That's we have to theoretically minimize the area, the surface area. Okay, that's what's formulas. We have to add all of the sides. We're still remembering that we have no top. It's open top. That's what we have. The area of the bottom will be 2x times x, right? 2x times x. And then we have two sides on the left and the right hand side, which will be x times h. And we have front and back 2x times h. Yeah, let's see, length times width is the bottom, the base. 2w and h and 2l, but I don't like my l and w. Okay. Length times width, which will be 2x times x, and then 2x times height, that's the, no, we have to be careful, x times h times 2. That means this is x times h, the sides, correct? And then it's 2 times 2x times h, which is of course 4. Please check if my surface area is correct. That means this is the behind the back side, and this will be 2x times h and times another 2x, like in the front. I will not mess up. That means it's 4x times h. Okay, good. Okay, that means just the first quantity 2x squared represents the amount of the material for the base. And now, as I said, this is just the amount of the material, the surface area. How can we create a cost function? We have to add $10 and $6. This and this. Okay, that means we can see, I don't want to mess up. That's amount for the base, and that's 2 of those quantity, the amount for the side. That's what I have to do, because 2x squared represents the amount of the material. And when I will go to the store, I have to pay, I have to multiply this by $10, really good. And the other one, I have to multiply by 6. That means this will be 20, that will be 12 and 24. I think math just, yeah? Oh yeah, we can, yes, really good. But since this is the same xh, 2 and 4 is 6, and 6 times 6 is 36. But when we add 12 and 24, I'm looking at the chat box, is the same. Okay, that's we can see now we do have a cost function. That means I would say this is, it's not, you will remember. But just, please do not forget the dollars, because sometimes we focus only on the surface area and we just forgetting the dollars. Okay, nice function. Still x and h, we have to rewrite probably h in terms of x. Okay. What we have? We do have this, that's the volume, because volume is 2x squared h and it's equal to 10, and I can solve nicely for h. Okay, that means h is just 10 divided by 2 is 5 and divide by x squared. And we will substitute here. Yeah, then we will have one variable function. 36 times 5 over x squared. X and x squared I can simplify, and I have to multiply 36 times 5. I just write that at the moment. Okay, one thing that is interesting here, volume. Yes, we can definitely do the other way. Oh yes, because you probably, Robbie, you probably realize that I'm always like choosing one of them, and actually we always trying to get the function in terms of x. We can solve the volume equation for x and have the cost function in terms of h. Yeah, but yes, that's the thing, because can you see the equation for the volume? 2x squared and h. When I will try to solve for x, probably the square root will be involved. Yeah, that's what we, but you can do either way, and as soon as you realize something is a little bit messy, then you can come back and find out the other variable. But yes, no, either way will be good. We always trying to simplify things, make the life easier than it is. Okay, that's when we do have this function. We have to, what I was going to say, this green circle, because that's my kind of like a restriction because of that 10 cubic meters. But do you think I will have any restriction? The h is defined as a 5 over x squared. X and h is positive anyway. That means theoretically x could be any number, of course, not 0. Yeah? We don't have this addition subtraction involved. That means x could be any number. Yeah, we can have really, really wide, like the length and the width, any number could be x. We don't have any restriction. That means x is just greater than 0, and of course h is greater than 0. No, which of course we have to find out critical points. Okay, we need the derivative. Derivative of 20x squared, no problem, 40x. And now we have 36 times 5, which we can probably multiply, 180. If you can help me, I think this is 180. Okay. Okay, but of course 180 is a constant. 1 over x. Do you remember what is the derivative of 1 over x? Because that I will include. If you can, yes, negative 1 over x squared. Excellent. And we can see negative 1 over x squared. I still didn't put 180. I don't know why. I don't want to scare you with the big numbers, but you can see if you don't want to spend time on your multiplication, you can keep it, because sometimes we can simplify, we can maybe factor out. Okay, I need critical points. That means in this case, we have to get a common denominator, which the common denominator, of course, is x squared. And I will just multiply 40x by x squared, and I will have x cubed. Okay, that looks better. 40x cubed minus 180. And of course, critical points are the zeros from the numerator and zeros from the denominator, but we will skip the zeros from the denominator because it will give me 0. X cannot be 0. It must be, of course, greater than 0. That means the only thing that I will focus is the 0 on the top. The derivative is 0 if the numerator is 0. And now, I'm still trying to make easier, but I don't know if this is easier, because we can definitely say 40x cubed equals to 180, and then x cubed is 180 over 40, which will be 9 over 2. Oh, that's definitely not a nice number. And I believe I've got the same thing I was just trying to be, I don't know, more helpful. Okay, but we don't have to. I factor out 5 and then I factor out 4 just to have, but I think 180 and 40 is much, much easier. That's we don't really have to look at my left-hand side. Okay, that's we have cube root of 9 over 2. It's okay, we will, because what is the question? Oh no, they asking what's the cost. Oh no, we will not do this because the number is not good. But what we have to do, we have to check if we have minimum at this point. That means let's just try to, did I add the slide? No, I didn't add the slide. Okay, that means I will put cube root of 9 over 2 and try to test, yeah, again, just in case if you have to solve the open-ended question. That means this is my, where is my derivative? I believe this is good. Yeah, I can just test this. When I pick small number, I will have 40x cubed, 40 minus 180. That means this will give me negative. When I pick bigger number than whatever cube root of 9 we can approximate, but that number is definitely, let's say, smaller than I can put 5, 6, 7. And if I will cube this, multiply by 40 minus 180, I will definitely get positive numbers, definitely. Okay, that means my cost function is decreasing and increasing. That means, yes, at this point, we do have minimum. And probably if you will end up with having this question, this is the only answer. I will not, because I can tell you what we have to do now. What is my cost function? The cost function is here, yeah, in terms of x. That means this is the cost function. And unfortunately, the question asks, what is the cost? What is the minimum cost? Saying faster, like faster. I have to take this x and substitute here. And we will not do this. That's too crazy because the x, we don't like the x value. That means this will be the minimum cost if x is cube root of 9 over 2. Okay? But we will just give the x value, the width. And 2 times that x value will be length. And of course, we don't even want to calculate the age. Okay, that means let's say x. If I would like to ask this question, I will only ask for x because it's, yeah. Okay, nice, yeah, nice question. And let's maybe do 1 or 2 more. I do have my next example, but I just, yeah, it's the same idea, but it's different shape. We will skip this question because it's the same. The volume is given. We have to minimize the cost through the surface area, but we can leave it like that. You can, at least then the answer is better. The radius is 2, but you can pause the video later and look at this. But let me do, oh, that's nice, multiple choice. Let's try to do this. Find the x coordinate or coordinates of the point or points on the parabola x squared minus 3 that is closest to the origin. That means on the parabola, we have to find the point that is closest to 0, 0. Can I draw this situation? We don't have to, but x squared minus 3. That's parabola shifted 3 units down. Right? This is negative 3. This will be actually square root of 3. Okay. And now we're looking for, that's the origin, 0, 0, a little bit too tiny. And now, where is that point? I don't know if my parabola is like draw properly to the scale. That means we never have to like assume, yes, we have to calculate. I don't know, I will assume that somewhere here, x, y, and since it's symmetric, is the same thing. That means probably that's the points. Yeah, I would say this. That means definitely the option B and C is not really a good answer. We will have the symmetric. Or maybe the square root of maybe the x-intercept, maybe they are the closest, I don't know. Yeah, like, oh, actually interesting, because I just draw it, yeah? The x-intercept, yeah, that's, now I'm just looking, maybe this is actually, I will use different color. Maybe this is the shortest. Yeah, this distance. Okay, of course, we will not guess. We may try to have the educated guess, but no, we will not risk 5 points on the quiz, or I think each question on the final exam is worth 8 points. That means we will not risk the 8 points. Okay. Okay, given information, just this, y equals to x squared minus 3. Looks probably too trivial, but it's nice because can you see we have y in terms of x? Yeah. Okay, required information. What we have to do? We're looking for the points, but in what scenario? Closest. Find the point that is closest. What do you think? My green, we have to, okay, minimize x. With, of course, we're looking for the x value that will give me minimum, but minimum of what? Yeah, I am at the 0, 0, and I have to reach the distance to the parabola. Distance, yes, that means we have to minimize a distance. Okay, distance formula will be the key. Do we remember distance formula? X sub 2 minus x sub 1, and the difference. Somebody said, yeah, Pythagorean, I mean, yes, kindly. Yeah, I don't know maths exactly what you mean, but yes, this is definitely involved. Okay, and let's actually find the distance, because we will have a distance between 0, 0 and xy. That means we will have x minus 0 and y minus 0. Of course, it's pointless to write 0 because it's distance between xy. I don't know where is the xy. Yeah, could be even this one. I can even say xy. Okay, but for this type of question, of course, we have to minimize the distance, but because of the nature of this formula, I think it's just enough if I will, how can I define this? It's just enough to focus on the quantity inside, because when I minimize the quantity inside, the whole square root will be also minimized. That means for the calculation, for the simplification, we don't have to carry the square root. Okay, that means please remember for the distance question, because it's obvious that if I minimize the quantity inside, the square root of it also will be minimized, will be small. Okay, that means just focus. I don't know how to write mathematically. I should say d squared because I kind of squared both sides. Okay, we can keep it this as a new function that I will minimize. Okay, that means the thing that I have to minimize is the inside quantity, which is of course the distance formula, x squared plus y squared. Yeah, I will just have a little bit like bold and okay, but we have to really rewrite y in terms of x because we need a function of one variable. Or maybe I can use, yeah, d squared makes sense. Okay, what shall I put in the here in the bracket, in the parentheses? I have to define y in terms of x. And we can see we don't have to do anything. It's of course the parabola formula. Thank you. Okay. Yeah, that means this is my function. I do have some restriction because all of the points they have to be on the parabola. However, the point could be anywhere. Okay, we can see x could be, because since domain for this function is all of the real numbers, Of course, we will not pick the numbers really high because that's pointless, but I don't have any restriction. Yeah? X could be any number. That means I don't have to be worried for the domain, only the critical point. Okay, let's find out the derivative. That means this is my formula and I am differentiating 2x, and I will use the chain rule. 2 times quantity to the power of 1 times 2x because derivative of the inner function. Oh, interesting. Let's simplify. That's my derivative. 2x, 4x, x squared minus 3. I can factor out 2x. Oh, actually, let's make it nicer. Let's distribute. 4x times x squared, 4x cubed, minus 12x. Oh, yeah, I think that will be better. Okay, that means the final formula for the derivative, this is derivative of the distance squared. That's the derivative. 4x cubed minus 10x. Yeah, do you think it's correct? Because we do have here 4x cubed minus 10x. Okay, derivative is 0 if 4x cubed minus 10x is 0. I can factor out 2x squared minus 5, and then x is 0, and x will be positive or negative 5/2 square root. Okay, and now the only thing that I would like to do, the test, I will try to squeeze it. Because we have critical number 0, we have a critical number negative square root of 5/2 and positive. And testing my formula, which is this one. Yeah, that's the derivative. Squared, yeah, derivative. Okay, putting big number positive. Putting, let's say 1 will give me negative, and the negative 1 will give me positive and negative. You can probably do it. That means distance behaves like that, decreasing, increasing, decreasing, increasing. Okay, that means we do have minimum at these numbers and maximum at 0 actually. Can you see when x is 0? If x is 0, y is negative 3. That means the blue dot will give me the maximum. Of course, the maximum distance. The maximum, hang on, you will probably think, why not picking the number? Because on the other one, I don't know. The values are going to the infinity. That means I don't have to detect, I mean, it's not possible to determine one finite number, but 0, negative 3 is my number that I can detect. This will give me maximum, okay? But minimum is definitely at these points. That's mean this one, okay? These numbers will be negative square root of 5/2, and we don't have to compute x. Again, because of, I mean the y, the corresponding y values. No, are you asking question? No, or maybe that was, okay. Because the chat box just, and you are the last one, okay. That's, we can see, we need the minimum distance. That means minimum distance is actually, yeah, my red intervals. I don't know if the scale is good, but the red intervals, red line segments are showing me the minimum distance. The green will be a little bit, yeah, the root 3 and positive and negative will give me like a little bit longer distance. Okay, that means distance is a good question because we can, and please remember, focus on the inside, don't carry the square root. And if it's multiple choice, probably we don't even have to do the test. But if I will ask you the open-ended question, okay, for the extra credit, please do the test, okay? It's kind of primitive, but it's, yeah, it's powerful. Okay, I think we can finish. I do have a few more. Okay, that's another one. Oh, that's another box. But no, let's finish. It's almost, 1 hour. I like that you have the camera on always. Yeah. Okay, and what we can do, that means you can practice. If you will need some extra help, please email me, because maybe I can run some recitation session, some practice problems. Of course, you're doing a really good job on the discussion, and you discussing between each other, which is really good. But remember, always check the session, always check the examples that I'm solving during the session, especially before the final, right? The review sessions are quite helpful. You probably know, because then you can ace it. Okay, I will let you go. Please stay strong and healthy. Practice this. And tomorrow, anti-derivatives. Please join me, okay? Thank you. Thank you very much. Thank you. Thank you, Noah. Thank you, Yatniel. Thank you. Justin, Chuck, Robbie, Matt. Thank you.